And so welcome to the Wednesday, June 28th, 2023 Joint Food Ontology Work Group call. And today we're going to be talking about planned processes and the difference between objective and mechanism in them. And Tarini will actually get to show us her more advanced work in this department. So I've left just the little outline there. And I see I've actually brought the wrong document. So I'm just going to go get the right document. The food process group, not the, oh, no, that's right. No, but I left the agenda for the call in the wrong one. So let me just patch that up just a sec. I'm not going to do that because actually tomorrow's group is more discussion on the topic. So in the food process specific group. So right. So I am sorry, just a little distraction there. Never mind. All right. So what we'll do is we'll start off with this presentation that both Tarini and I gave a little bit earlier to the food process group, and I will share my screen. And begin. So everybody can see that.
Yep.
Okay, great. So this work stems from last year, Trini and I getting together and trying to think this upper level ontology, process modeling ontology through, and now the process ontology work group is focusing on this very same content every second Thursday. Where this work ends up ultimately still has to be decided, whether it's food on itself taking on a number of these classes. OB wants to take on a number of these upper level classes, but we have to convince them which ones if we go that route. Or perhaps a chunk of this food process ontology sits in its own ontology. So that remains to be determined. But what is for sure is that there's this distinction between the how and why, action and objective of planned processes. So we're going to get into that. So what we perceive, to get rid of some of this stuff, yeah. So what we perceive, what the framework we're working within is this plan process, OB plan process, with its specification, which has an action specification part and an objective specification. And we translate this into having a process by objective branch by which processes can be categorized. And in those, you can measure success of the process by looking at the output material or data to see if it meets some objective criteria. And this can also involve a little bit more subtle formulation for getting to the output. A 3 or 4 minute egg is an example, where maybe you're not testing the egg, but you're measuring some time out under the process conditions in order to achieve the goal by a formula. And also you can be measuring amounts of resources expended besides time. But in all cases, it takes time to achieve the goal. Now, if we're looking at a process just by mechanism, the how, its objectives, it has objectives not to be broken, but they're relative often. So the heating of water that increases or decreases a characteristic, reducing a particle size, heating, raising temperature. And there's no cutoff or change threshold. So yes, temperature might be raising in a relative objective, but you haven't said when the process should stop on that condition. So this invites a study, a more detailed study of material processed by mechanism, where we've got various upper levels that Trini and I identified, but these are subject to feedback and working. But we came up with simple things like material separation and material combination and material containment. And then more complicated things like energy modulation and force modulation, and then looking at the molecular mechanism by what kind of reaction and where in a material it's happening. So the mechanism involves the application of energy, force on solids, liquids, and gas, and then this macro micro level distinction about where the activity is occurring. And the motivation for making this distinction between objective and mechanism arises here because we want to perceive that there are different paths, mechanistic paths for achieving some set of objectives. The other thing that's going on here is a lot of this stuff is being defined above the level of food. So we're actually aiming for a general process, material process upper level. Okay, so a little bit more of this is actually a bit of a repeat of content before, so I'll gloss over it. Just to say that in material processing by mechanism, we mentioned there are no cutoffs like time, temperature, particle size limits, but there might be a rate of application of the resource, like frequency of chopping, mixing that can be specified. Now, the bi-objective branch gets us into the details of how to specify change in an output material, measuring it, and that's necessarily involves, if not some formula, some sensing of an objective. So a process by objective has this part, sensing an objective often, and it's also measured. It can be measured directly as the material change in the output, but it can also be measured. There can be objectives that are present, such as greater efficiency of the process that might make you choose one process over another in terms of its mechanism. So there are just some examples on this slide of, say, fractionation by objective, the fractionation to achieve a distinction between milk and cream as an objective, for example. The material processing by cooling, you might be cooling for some sensory effect, like chilling or freezing for ice cream. And then we finally now do get into this food processing by objective, and that's where there can be health objectives involved or other kinds of sensors, organoleptic sensors. So the distinction, of course, enables us to actually place processes under both hierarchies, and this is an example of that. So you might have a heating process, mechanism with no end to it, a boiling process, mechanism with a specific end, namely whatever liquid at its boiling temperature. And then boiled water can be the objective. Boiled water here expressed as like a material output under some condition. Now, if you look at boiling in a stovetop, it can be satisfying both boiling of water from an objective perspective and the heating of some container. from the mechanism perspective. Same with boiling in a microwavable dish. So you get these choices coming up. And so what Tarini is going to do a deep technical dive in is coming right up, and that's where we're focusing on food processing by sensory objective, either instrumental or human perceived. And this food processing by objective can also involve other goals, such as nutritional component addition, or taking some chemicals away out of the food, and food safety. But we will, oh yeah, right. So here's a closer look at the sensory objective. You can see a food material has some quality, some mouthfeel quality, and then some assay to determine the mouthfeel quality. This can be a sensing by human. And then you got other things such as kinematic viscosity assay, sensing a kinematic viscosity characteristic or quality of a food material. Okay, so this takes us up to where we get to see Tarini's stuff, and I'll just turn off recording for that pesky paper thing. Now, Tarini, we'll just switch over to you for your slides, okay?
Yeah.
Okay, so I'll stop share.
Okay.
I'll...
Yes. Hey, good morning, everybody. Tarini, awesome stuff like usual. I am curious to know a little bit more about the machine learning part of this. Could you maybe say a little bit about what kind of data you fed in, and then what kind of processing you did on the data to get what kind of outputs? Maybe just at a high level, if possible.
Yeah, sure. Yeah, of course. So I used for this data, it was it was a regression model, because you have like one and yeah, I mean, sorry, so if I'm kind of giving an explanation like in a classroom or something, I don't know how much you know, so I'll just talk very basic, and then I'm happy to change my explanation. So generally in a regressor, you have, the one output, the Y, and then you've got a bunch of X's, 100 X's, 500 X's, whatever. And, generally in machine learning, of course, you have like a very large X vector. So, and each of this X vector, the data, every in the vector X1 to X500, there's a value. Now in the machine learning model, you've got like a network of nodes. And so basically as you train it, the network of nodes is being assigned a weight. And so there's the way that what that network in the middle looks like tells you the different kind of model. The random forest really made sense for this. And what random forest is that it's a bunch of different decisions being made. So you're saying if that, for example, here, the chain length is this and this, but it is, it's greater than this, but it's less than this, then the gelatinization temperature will be this, else the gelatinization temperature will be this. So random forest is just many if else then kind of like trees. And because it's so many variables, you need machine learning models to do that. So the model here in the center is random forest. Now, what you have to train is how many decisions need to be made, right? So what is the depth and what is the breadth of this like if then else structure? So it's basically a tree. That's why it's called a random forest, because there are many trees in this model and you're making that decision. So that's the first step. You figure out what is exactly the right breadth and depth of the trees in the random forest model. And then once you have that, once you know what the model really looks like, then you need to start finding out the features, like in this decision tree, where is the most important decision happening? And then what is the accuracy of that? So it turns out that sometimes there's actually there's always a certain number of optimum features that are important for the decision. And if you've got, sorry, you've got a delivery, just a minute. I'm so sorry to interrupt this explanation.
Well, while Tarini's stepping away, just a quick observation. The predictive power and the math of this has to do, of course, with how we set up the data set and where and what we feed it into for what kinds of analysis and to do what kinds of regressions. The ontology part of this has to do with what do we name the columns in the spreadsheet, so to speak, which is another thing I'm curious about, but it's a separate line of discussion, you know, the sort of the structure of the data we feed in, and what kind of work needed to be done to get data sets from different sources to talk to one another so you can stack them all on top of each other to feed them in. Just a thought. Cool stuff though.
Well, that's a good
Okay. Sorry, I can't turn on my video. Anyway, can I pick up from what I was saying, or do you have a different question now?
Thanks, Tarini. Already that was helpful, but the idea that that you fed in data in order to run regressions using a random forest style of machine learning.
Yeah.
I mean, I've got some follow-up questions, but that gives me a sort of high level to get started. Thank you for that. I'll let other people chime in.
One other question that arose from that was whether, in linking to external data, Tarini, were you able to take advantage of any like an ontological attitude, or for all the external data points, were you just making sure that your spreadsheet column names lined up without having to get into the whole ontology business of things?
So what was your question? Sorry, Damien.
Right. So in your work, have you come around to cross-referencing external databases yet? In terms of your own experimental data?
This is not my external data. This is actually from a scrape from literature. So yeah, and there are no other databases. So this would be kind of the first really organized like data and structured data. You know, so like that's where the ontology terms really come in, is that it is like, I mean, of course, you know, it's not like gelatinization temperature is like an unknown word, but sometimes it's also referred to as like, you know, enthalpy or something. So there are different words, they all mean the same thing. So I think, of course, the work that we did is not complete, but it was a good starting point, was never intended to be complete. So I think that language is very important for structuring the data.
So you literally were dealing with databases from literature that had different column names for.
Yeah, there are different names. Yeah.
So your ontological journey began.
Well, there's a lot to do there, but I think what's really important is like from a high level is this sort of objective mechanism, like what is the measurement? So for instance, the physical properties are kind of, you know, they're really measuring the mechanism. Some physical properties measure the mechanism, some of them measure the outcome. And this was really important to understand, like, what are the X's and what are the Y's? You know, it would make sense that the mechanism are the X's and the objectives are the Y's. So yeah, like that's why the sort of the mechanism objective fits very well to like the structure and the function.
Okay, anyone else bring something forward? Have other people done some similar technical work in other areas besides gelatinization? That is actually one side comment. The food process ontology work group that we have could use a few more food scientists in it. We have a chef and we have lots of ontologists. But besides Tarini and her deep dive here, we need to encourage a few more food scientists into the group.
So just a comment on the data modeling, and actually then I do have to go, but I would be happy to send this paper out because I realize there's some of you could probably make very insightful, give some insightful feedback. It may just have been a lot of like new terminology. So I'm happy to send the archive version of this publication, and I'd be happy for any feedback. So just one more thing is, I mean, what I realized that I wouldn't have even known is that this work of data modeling, I mean, of course, there could be something very complicated. As soon as you get into multiple biopolymers, it becomes complicated. But it was actually very interesting how simple this was, that, you know, just knowing a little, I would not call I'm a good user of machine learning. I'm not an expert, but based on my little knowledge, just applying a random forest, and it also seemed very intuitive, just having many of these very complicated, but essentially if then else kind of decision making, it fits so well to this data. And so actually, you know, the biggest challenge was the vocabulary, getting the data, and then actually the modeling, which is maybe a revelation here, but the modeling was actually not that difficult. So I think that not having the data kind of, you know, is more of a mystery. Like, you know, does AI really work? I feel like the bottleneck there is having structured data, and then actually it works really well. I mean, that's been my experience.
Yeah, completely agree. And that's my experience. And I think the experience of a lot of people. I think a lot of people think AI is going to be the solution to all our problems, not realizing that if you don't have well-structured data that has some sort of vocabulary or other vocabularies mapped to other vocabularies where there's been a lot of thought put into what the categorizations are and their structures, then yeah, anyway, I think my point is being made. I'm just echoing what you're saying. And I don't think you're the first person to make that observation.
Yeah, no, really. Yeah, thanks for echoing that. And actually, I do have to leave. I've got a fridge delivery and they just won't wait, and I'll be left with a non-functioning fridge. So I have to go. I will send a paper, and I look forward to your comments.
Okay.
I guess my last question is not going to happen, but I'll follow up with her.
Yeah.
But it was very interesting. Thank you very much, Damien.
Yeah, you bet. Yeah, and handy, you can always feed back to the group a month from now if you get a juicy response from Tarini.
Damien, just one more quick closeout comment on Tarini's work. I'm guessing that our food processing work group could usefully use the data set from this paper, from this analysis, as an example of some food process data in its natural environment. Like when these rice labs recorded the cooking of rice, what were all the variables that they used? What did they call cooking, right? What is the name of the variable there? What are all the other metadata variables that came along with it? Just as a sort of, an example of sort of live stuff that we need to be able to reckon with.
Absolutely, yeah. Our deep dive should be able to generate all the terms that Tarini needs to support her data management around this, and the model too, which is, I guess, one step beyond. Okay, well, that sounds like a good point, which to wrap it up for this week and this month. And we don't have anything scheduled for next month. Looks like summer holidays and conferences start colliding. So I will take a stab at creating a schedule for the fall in a month or two. Okay, folks?
Thank you so much.
All right. Thanks a lot. And talk to you at the end of summer.